It's a pleasure to be back at the Graduate Center again. I first met Sergey back in 1994 at the St. Petersburg meeting that was talked about in Anil's talk. And I've always admired the breadth of Sergey's work, and hopefully that you will find this similar in terms of bringing in lots of ideas, of different sorts of ideas. This is joint work with a student of mine, Alex Brick, who comes from an unusual program for me. One of the things, I'm the Associate Dean of Physical Sciences at UCSD, and so one of the useful things that I did was help to start a program in computational science. So Alex is actually a student in computational science doing computational logic, and it was part of his work in computation that sort of led to this idea. So this idea is, I'm first going to talk about answer set programming, and then what I'm going to talk about is a significant extension of an answer set programming. So this answer set programming is an expressive knowledge representation formalism. The key is that it has a sort of non-classical negation operator, often called negation is failure, which allows you to model all sorts of interesting phenomena, incomplete information, framing axioms, default assumptions, something called the closed world assumptions. It usually has the ability to make this much easier and much more compact than compared with typical first order representations of the same things. Right now it sort of supports aggregates over finite sets and more generally constraints over finite sets. And its basic idea is that, like Professor Merrick talked about, the idea is you're going to write down a bunch of constraints about the possible solutions you want, and then you're going to turn it over to a solver to go find all these solutions. This term answer set programming was actually coined in 1999, but around that time several people realized that if you look at the complexity results, you really should think of the search for what I'm going to define as stable models is really to solve sort of search problems, and that's really its advantage. One of the things, so let me say a little bit about the basic idea. Professor Merrick talked about this briefly in his talk, but the typical logic programming rules is basically saying you have A1 through AN as you derive those, and you haven't derived B1 through Bn, whatever derived means, or you don't have any information about this, then you can conclude A, right? So I'll talk about the head of clauses, the body of the clauses. There's the positive body, which is this is A1 through AN, and the negative body, which is the part that's negative. Now this is not classical negation. This negation is full a failure kind of negation. And a program is just a collection of these, and I'm assuming that C's and the A's and the B's are just propositional atoms in this case. So this is a propositional case. Okay, so the typical thing that people have is form programs, and those are really easy to understand for logicians, right? We know that there's going to be a least model. There's a one-step provability operator, which is you apply the one-step provability operator, you collect all the conclusions for which the body of the clause is an M, okay? And this is obviously a monotone operator, and so it has a least operator, and you know, the least model of it is going to be important for us, but in general, fixed points are called supported models. Okay, so now is really the first crucial concept, which is the notion of a Gelfand-Lifshitz transform. So the question is, how do we sort of interpret these? If I have a program of these clauses that contain negation, what am I going to do in terms of trying to figure out what models are? So the idea is this is a sort of guess and check mechanism. You guess a model, and now you look at the clauses, and you say, well, any clause that sort of disagrees with my model, I just throw it away, right? So if I have a B that's in my model, and this clause says not B has to be not in the model for misimply, well, I just throw it away. I don't care. And then for each surviving clause, I'm just going to throw away all the negated atoms, and now I'm back to a Horn program. I get a collection of clauses that's a Horn program, and that has a least model. And if that least model agrees with M, then I call it a stable model. So these are the basic objects that we're going to search for. This is a bit, I sort of view this as a semi-honest politician's version of things, which is anything that disagrees with my point of view I ignore. The semi-honest part says, well, after I ignored all the facts that disagree with me, I at least should have a justification for everything else that I believe. In other words, I should be able to rederive from the clauses that I kept, right, reasons why everything is in there. So this is the basic idea, right? We all know that this isn't true about politicians because they don't do either side, so it doesn't make any difference. So they're not interested in this sort of thing whatsoever. So this is the definition of the stable model. You do this elimination of clauses, and you come back and you ask that the least model of the horn clause that results from this reduction procedure is the model you have. So just for example here, I'll do a very simple version of a program. So here's a program. Look at M. What does it do? Well, if you look at the clauses, of course the bottom clause is just the horn clause. You're never going to touch that. But the other two clauses, B and D, aren't in there, so essentially you get to replace them. You just get to eliminate them. They don't get eliminated by this process, right? And in this case, from this, you can easily see that from these three sets of clauses, I can get back A, B, and E. And so M, A, C, E is a stable model, right? But it could be that you get too much. So the same clauses would hold if I just took the model CE. I'd get back the same set of clauses, but now I generate too much coming back, and so that's not stable, right? And I could go the other way. I could derive too little after I do this process. So here's an example where because B's in there, that first clause goes away, and now I only have the bottom two clauses.
You're going a bit fast.
Right? Okay, so in this particular case, B's there, so the first clause gets eliminated. Right? The other two clauses stay the same. D is not in there, so I just replace that by C, and E goes by C, then nothing's ever going to touch that clause. But now out of these two things, I just get C and E, so I don't get back the whole model that I got. So when you do this elimination process, you're asking, it could be that you get too little, it could be that you get too much, and this is sort of, the three-bear situation. You want to get it just right. Okay. So this is what we came to know, and there were lots of choices for possible semantics for this. And this is pretty much the community that in non-monotonic logic and answer set programming is pretty much settled that the stable model semantics is the correct semantics for this sort of stuff. It's also very flexible with respect to extensions. And so now I'm going to talk about using the same idea, the Gelfand-Lifshitz transform, for an extension which I'm going to call hybrid ASP. But before I do that, I should point out that while this negation is not classical negation, it's not used the same way, there are tricks to get back negation. Okay, so here's a kind of way that you impose constraints in an easy way. So let me go through this. So suppose I want to sort of eliminate models that have A1 through ANM and that B1 through BJ are not in it, right? So basically I'm asking for the negation of this body to hold on the right. And the idea is to pick a new atom, right, A, which hadn't appeared in the program before, and construct a clause of this way that says not A, these are sort of part of the body, and this is going to apply A. And now you ask, could I ever have a stable model, right, which has A1 through AN in it and B1 through BJ not in it? And the answer is, well, if you did, then the key question is asked, could A be, is A an M or is A not an M? Now, if A is an M, then this clause is going to get eliminated in this two-step process. And if that's the only way you can derive A, then you're not going to be able to get back A, so this is not going to be a stable model. On the other hand, if A is not an M, then this clause is going to fire, because then when you reduce it, all of this part is not going to be in the model, so now you're going to get a version that says A followed by A1 through AN implies A, and since you're assuming somehow A1 through AN got in the model, then at this point some A will get in the model, and you've derived too much. So the effect of this is basically say you can't have a stable model where you have A1 through AN and not B1 through not BJN. It's a way of it's a tricky way to do negation, if you like. So you still have that expressibility, but in a slightly different way. But only in the search for stable models. Okay. So I went the wrong way. Okay, if you want to put this in predicate logic, well, you know, you just have the same set of clauses except they're now atoms in predicate logic. You assume that you think of these as universally quantified. So what do? Well, the basic idea is you take a clause like this and you ground it, which means you replace all the free variables by terms, and so now you get what's called the grounding of P. And a ground instance is when you replace all the free variables by terms so that you end up with something with no free variables. And now if you take the collection of all the grounding of all the clauses, you're really back in the propositional case. And you basically say, well, a stable model of the original predicate logic program is a stable model of this ground program. So you reduce it down to the propositional case. Okay, so this is the basic idea of this. You can look at the complexity of these, and it makes a lot of difference as to whether you allow function symbols, at least in the predicate case or not. It makes a tremendous difference, right? So finding the least model of a finite home program, propositional logic, that can be done in linear time. If you ask the same thing, what's the least model of a Horn program, you know, with function symbols, then it can be an arbitrary recursively enumerable set. Okay, so here's a big jump in complexity. It even gets worse when you add negation. So the question of whether there's a finite propositional, whether a finite propositional program has a stable model, and unlike, you know, first order logic, you know, you might not have stable models. In particular, if I go back, this clause that I was doing here, if there is no A1 through AN, if you just have the clause A arrows not A, well then there's no stable models whatsoever, because, you know, then I have no condition on the models. You can't have A in the model, because then you eliminate this clause and have no way to derive A, and you can't have not A in the model, because then A gets derived, right? So that way, just here's a case where you can have a program that has a stable model, you add an extra clause, and now it has no stable models. This is why it's called non-monotonic, because you add more facts and add more clauses, and you can get less. Okay? All right. So, so you have this question of, you know, whether there exists, given a finite propositional logic, does it have a stable model? Well, that's known to be NP complete by Merrick and Trzynski in 1993. And if you add function symbols, then the question is sigma 1,1 complete, right? So that's a pretty big jump. So basically, you know, these sorts of negative results about function symbols convince people, like in the database community, those functions are bad things. They make the complexity go way up, so let's just ignore them. And if you look at what are now the solvers that people have, and this is what Professor Merrick was talking about in his talk on Wednesday, you know, there's a lot of solvers that are quite useful. But they don't allow function symbols. They do allow some aggregations over finite sets, but things like dealing with infinite sets, numerical algorithms, statistical reasoning, none of them do this, right? So the thing I'm going to talk about in the time that's left is at least one proposal where you can think of extending this framework so that you can do this sort of reasoning. Okay, so what was the motivation for this? As I said, this student was doing a lot of simulations, and if you look at a lot of simulations of, various physical properties. There's people at UCSD who do models of dog's heart and that sort of stuff, or tides and, all sorts of physical processes. And typically they'll sort of have a set of parameters and they'll solve a differential equation, an integral equation, and they'll advance the system to the next time step. And then maybe in some regions they'll have to change the modes in which they're doing the approximation to a different differential equation, a different integral equation, right? And the logic of when you switch modes is not explicit. It's built into the program somehow. So we were trying to figure out a way to have our cake and eat it too, so that we could do some numerical algorithms but have logic be the controller, if you like. Okay, so to do that, you sort of have to significantly extend what we normally think of as a logic rule. So we normally think of the logic rule as we have some hypothesis and we get a conclusion. And what I'm going to do is to say, well, in addition, there's going to be some algorithm which is going to advance the system to the next state, which the logic is going to tell me whether it applies, and I'm going to use that to generate a new set of parameters and maybe some associated facts that are supposed to hold at this new set of parameters. So the model that you should have in mind is a very simple one. So anybody who's seen a James Bond movie, right, has, the opening credits, he's usually skiing downhill or going downhill in some car, and, people are shooting at him, and then his car turns into a boat, and then he gets away, and all this sort of stuff. So the question is, well, this isn't a movie, so this is the best I'm going to do for this. But I think of yourself as sort of going downhill. There's various slopes that you can go downhill. Then the car can turn and go across a lake, and then maybe goes across a desert, and maybe in this lake there's been different currents, so you have different regions here. And the idea is that every delta seconds, the agent has to make a decision depending on the situation that faces him, right? In other words, are people shooting at him, or is he trying to just get the girl at this point, whatever, right? Okay, so this is the model to keep in mind. So if we think of how we would describe the position of the agent, well, it would be a mixture of some continuous variables like time and position and acceleration, velocity, but there's also some discrete variables. In other words, is the car set up to be a car? Is it set up to be a boat? Whatever, right? So I'm going to call these sequence of positions generalized positions. And I'm also going to, at least in the first pass, I'm going to say, well, what is going to happen is I'm going to go from a generalized position, and it's going to advance delta seconds where delta is fixed. And so every position here is going to be of the form, it'll be at some time k delta, and I'll have some set of parameters here. Some would be discrete, some would be continuous. Okay. So this is one thing. So I have this parameter space, and to keep things simple, I'll always think of the first coordinate as time. Okay, and so if I talk about t sub p, I mean whatever the time, that's the first coordinate. If I want the ith coordinate here, I'll talk about x of I sub p. And I'll generally refer to these as generalized positions. The second ingredient will be I have a set of atoms. So this is just like in propositional logic. And then I'm going to have my underlying universe be atoms cross generalized positions. Okay. So what's going to be a model? Well, a model is going to be now a subset of atoms cross generalized positions, and I'm going to say that it satisfies, M satisfies A sub p, just in case A sub p is an element of M, for any given generalized positions, and a given set M, you could talk about the set of all atoms for which A and that holds at that generalized position. We'll call that the world of the positions. And if I have a sort of typical logic programming calls, it's the usual sort of thing. M satisfies this kind of clause at position P, just in case AIP is in, so all the hypotheses hold at that general position. and none of the BJPs are in there. So this is the same sort of thing that you did in the basic logic programming class. Okay, so now what are you thinking of the rules? Okay, so I'm going to talk about what I call basic hybrid programming, which is the simplest version, and then I'll generalize it in the next couple of slides. But, think about James Bond again, right? And depending on what the situation is, which are modeled by these atoms, right, I want to associate two other things with this. There will be an algorithm that's associated with it, which is what A is, and there will be O, which is, if you like, the set of regions, the set of positions which you think this rule could possibly apply. So again, go back to this thing where there may be different currents in the lake, so that you want to have different rules depending on what the current is. Then O is sort of controlling the set of positions where you're going to apply that particular rule, right? So it's a restriction on the rule. And basically, what it does is it is going to, when I apply this at a generalized position, assuming that that generalized position satisfies the body of the clause in the sense of the previous slide, then I'm going to apply this algorithm, which is going to give me a new generalized position. In the case of basic hybrid SP, I'm going to assume the new generalized position, the time is just increased by delta, right? And it's going to tell me at that new generalized position, A is supposed to hold. So this is what this rule is supposed to do. Okay? You also have, so the key here is that this algorithm is totally general. I do not want to think of this as, something that is defined in some logic or that sort of thing. Because I'm interested in where A is solving a differential equation, A is solving some optimization problem, something like that. It's anything that can advance this, right? So this is quite arbitrary. And as I said, the key in basic hybrid HP is that if I have a position, then I'm going to assume this algorithm produces another position at the next time. And in this case, I'm going to assume it's a function, so given a generalized position, it produces one new generalized position advanced by delta, a time step delta. Now, in addition to this, we have what were called stationary rules, which are things where you could drive some more facts at a given generalized position. Okay? So it's the same, it's almost exactly the same as we had the rules before. There's no advancing here. There may be a set of positions. There's an O here, which is telling you the region in which this rule applies, but it basically says, now it looks exactly like a logic programming rule, just written in different form. And the reason we write it in this form is because it won't fit on the page if I don't do it one over the other. But if I was writing this in logic programming form, I would have an arrow A instead of this usual bar situation. So these are sort of just typical logic programming rules relative to a fixed world, if you like. Okay, so these are the two types of rules that you have. There's some problems with this, right? So in more complicated situations, do you really only want to advance fixed delta second?